Hey everyone, my name is Max Disler, and I am a third-year PhD candidate in the Department of Chemistry at Northwestern University, and I work under the guidance of Professor Chad Merkin. I am originally from Northern New Jersey, and I earned a bachelor's degree in chemistry and neuroscience and behavior from Wesleyan University. Outside of the lab, I enjoy writing music and swimming. Nanoparticles are defined as a material that has at least one dimension between 1 and 100 nanometers, or 1/1000th of a meter in size. To give you an idea of that scale, a tennis ball is 100 million nanometers in diameter. A period in Times New Roman 12-point font is 1 million nanometers in diameter. Human cells are 10,000 nanometers in diameter, a typical virus is 100 nanometers in diameter, and a simple glucose molecule is 1 nanometer in length. Nanoparticles can be made from metals like gold and silver, semiconductors like cadmium selenide, glass, and many other materials, and they can come in different shapes like spheres or cubes. From the color-changing skin of chameleons to the stained glass windows of cathedrals to the energy-converting layers of solar panels, nanoparticles can be found in nature, used in art and architecture, and applied in many modern technologies. Due to their small size, nanoparticles have properties that are different even from a bulk sample of the same exact material. Scientists are striving to understand the unique features of nanoparticles and control their assembly into ordered structures with unique properties and functions, including advanced materials that can diagnose and treat disease, transmit information, separate gases, and generate and store energy in new ways. But directing nanoparticle assembly is not a simple task. It requires a vast chemical toolbox in order to assemble nanoparticles from the bottom up, placing nanoparticle building blocks into structures that are bigger and more complex. Imagine, for example, that nanoparticles are like Lego building blocks. Individually, they each have their own size, shape, and composition. But when combined with other pieces, they can form larger, more complex, and functional structures. This idea is the foundation of bottom-up assembly, and it is a powerful approach to creating new materials. But how does one control not only the features of individual nanoparticles, but also their locations relative to one another such that we can build new materials with nanoscale precision? The Merkin Lab has developed new chemistry to do just that. Just as atoms are the building blocks of conventional matter, nanoparticles are the fundamental building blocks of many modern materials. And just as bonding interactions between valence electrons allow atoms to interact to form molecules, bonding interactions between DNA strands allow nanoparticles to interact to form programmable matter. Now, a question you may be asking yourself is how can DNA, the blueprint for life, be used as a smart glue to form modern materials? Well, one amazing feature of DNA is its chemical specificity, or its ability to recognize and bind with a complementary strand facilitated by hydrogen bonding between base pairs A and T and G with C. Specifically, if we mix two sets of nanoparticles functionalized with complementary DNA sequences A and B, then DNA A and DNA B will bond with each other, and the nanoparticles will be carried along to form highly ordered extended assemblies. Since modern chemists can synthesize DNA of any sequence and length easily and quickly in the laboratory using a machine called the DNA synthesizer, we can achieve unprecedented control over nanoparticle bonding. These nanoparticles, functionalized with DNA, are referred to as programmable atom equivalents, or PAEs for short. Many analogies can be drawn between traditional atoms and programmable atom equivalents. Consider common table salt, or sodium chloride. We know that the electrostatic affinity between positively charged sodium ions and negatively charged chloride ions results in the formation of crystals where the atoms are arranged in a face-centered cubic or FCC array. Similarly, DNA bonding can drive the assembly of PAEs into a vast array of crystal structures, some as common as FCC, but also others that have never before been seen in nature. However, a key difference is that, unlike atoms, the structure of PAEs is highly adjustable. Therefore, scientists can precisely tune PAE bonding. In other words, while atoms have inherent bonding characteristics based on their electronic makeup as dictated by nature, PAEs have tunable bonding characteristics based on the nature of the DNA shell as dictated by, well, the scientist. This fact makes PAE bonding core independent, and it is a fundamental departure from conventional chemistry where the choice of the atomic building block is linked to the mode of bonding. This gives us greatly enhanced possibilities in material design. Current research continues to push the boundaries of this field. For example, we are synthesizing new types of PAEs in order to expand the PAE periodic table. Like atoms, PAEs can be cataloged. We can do that based on the size, shape, and composition of the nanoparticle core, as well as the length, sequence, density, flexibility, and backbone of the DNA shell. A table like this can have near infinite number of entries, and allow scientists to discern trends pertaining to these nanostructures, much like the periodic table allows for atoms. In my own research, I am building new types of PAEs using DNA with dynamic rather than static chemical structures, allowing me to toggle how PAEs engage in bonding in crystalline lattices. What I love about research is that every day I have the opportunity to solve problems. Whether it's troubleshooting an experiment or coming up with an innovative approach to create new materials, I'm constantly working to push myself and society forward. My undergraduate research experience taught me to work hard and think critically, preparing me for graduate school and for life. The earlier you learn these skills, the better, which is one good reason to begin research now as an undergraduate. I hope this video helps inspire you to start on your journey.